Good morning, everyone. We are going to the section on axiomatic approach to probability. And before going to that, we need to know certain facts about functions. As you all know, function, usually represented as y equal to fx, is a relation between two sets. The set from which x takes its values is called the domain set, and the set from which y takes its values is called the range set. So actually, the function y equal to fx is a relation between the domain set and the range set such that there is a unique value of y for each value of x. Functions can be of different types depending upon the members of the domain and the range set. It is not absolutely necessary that functions should always deal with numbers. Functions can deal with numbers, they can deal with living things, they can deal with non-living things, anything according to convenience. Now consider an example, y equal to x square. So this is an example of a numerical function where x and y can both take real values. Suppose we give the values 1, 2, 3 and 4 to x. The corresponding values of y will be 1 square, that is 1, 2 square, that is 4, 3 square, 9 and 4 square, 16. So for this function, the domain set or the set of values of x will be set 1, 2, 3, 4, and the range set, that is the set of values of y, will be set 1, 4, 9, 16. So the function y equal to x square is an example for a numerical function. Now consider another function y equal to fx, where the function is defined as fx is defined as the father of x. Clearly here x means a child and y means its father. So the domain set or the set of values of x will be a set of children, and the corresponding range set, that is the set of fathers, set of values of y, will be actually a set constituting of their fathers, because here the relation is y is the father of x. So here the range and domain set, they don't have numbers as their members but something else. Now consider another function y is equal to fx, where fx is defined as the capital of x. Clearly x can be a state or a country, and the values of y will be their capitals, that is it will again be the names of certain cities. So here both D and R do not have numbers as members, but instead of that they have some states or the names of certain places. So depending upon the convenience, we can define a function in any way that we want, and depending upon the function, the domain and range set will be continuously varying. Now we are going to study certain types of functions. These types are based on the way the domain and range set are defined. The first type of function that we have to study is a real function. A function is said to be a real function if the range set R is a set of real numbers. So if the range set means the set of values of y. If the set of values of y, or if y takes only real values, we call the function as a real function. The next type of function is called the non-negative function. A non-negative function is a function in which y takes non-negative numerical values. So if y takes real values, it is called a real function, and if y takes non-negative values, when we say non-negative, we include all positive numbers and 0, all positive real numbers and 0. So if y can take all positive real values including 0, then we call the function as a non-negative function. So a function can be called a real function and a non-negative function, or a real non-negative function if the range set R constitutes of all the real numbers belonging to the positive plane. Now we are coming to another type of function which is called the set function. Here, a function is said to be a set function depending upon the elements of the domain set D. See, you have to understand one thing. The term real function and the term non-negative function were both connected to the range set. That is, here, suppose when we consider our first example, the range set R is set 1, 4, 9, 16. Clearly, all the elements of R are real numbers. All the elements of R are positive numbers. So, we can call this function y equal to x square as a real valued non-negative function. Now, coming to the next type, that is set function, here the concentration is on D. That is, it is on the domain set, or it is on the set from which x takes its values. Consider this example where D is defined as a set of some small sets. That is, here D is a set of sets. That is, it constitutes of one set 1, 2, then set 3, 4, 5, and then set 6, 7, 8, 9. So, D is a set of sets. If for a function we have the domain set D as a set of sets, we call that function as a set function. So, this is the third term. The first term was real function, next was non-negative function, and the third one is set function. Consider this function y equal to fx, where fx is defined as the number of elements of x. Clearly, x is defined on D, that is, x can either be the set A or the set B or the set C. So, depending upon whether x is A, B or C, the values of y will be either 2 or 3 or 4. So, the range set here is set 2, 3, 4. Just think of this function. This function, for this function, the domain set D is a set of sets. The range set R constitutes of real numbers, and that too positive real numbers. So, we can confidently call this function as a non-negative real set function, or a real non-negative set function. Now, the fourth type of function that we have to study is a totally additive function. A function is said to be totally additive if this condition is satisfied. That is, for any two elements A and B, f of A union B is equal to f of A plus f of B. Consider our previous example. Here, A is equal to set 1, 2, B equal to set 3, 4, 5. So, A union B is equal to set 1, 2 union set 3, 4, 5, which is equal to set 1, 2, 3, 4, 5. So, what is f of A? F of A is the number of elements in A. So, f of A is equal to 2. F of B is the number of elements in B. So, it is equal to 3. And f of A union B is the number of elements in A union B, which is equal to 5. Clearly, 5 is equal to 3 plus 2. So, for this particular domain set, our function y equal to fx equal to number of elements in x is a totally additive function, because for this example, this condition is satisfied. So, our function y equal to fx is equal to number of elements of x is actually a non-negative real valued set function, which is also totally additive. So, understand, a function is said to be real function when the range set has real values, is said to be a non-negative function when the range set has non-negative values, is said to be a set function when the domain set is a set of sets, and is said to be totally additive when this condition, or this is actually a two event condition or a two element condition, we have to generalize it as f of A union B union C union etc. is equal to f of A plus f of B plus f of C plus etc. And if this condition is satisfied, the function is said to be a totally additive function. Thank you.